Our speaker tonight, we're very excited to have her here. She's actually in town for a conference, and it worked out well that she had some free time to get down here and talk with us during her visit. I'm going to read you her bio real quick. This is from the NASA website. Dr. Amber Straughn is an astrophysicist at NASA's Goddard Flight Center in Greenbelt, Maryland, and serves as the Deputy Project Scientist for the James Webb Space Telescope Science Communications. She grew up in the small farming town of Bee Branch, Arkansas, where her fascination with astronomy began under beautifully dark rural skies. She obtained her BS in physics at the University of Arkansas in Fayetteville in 2002 and completed her MS and PhD in physics at Arizona State University in 2008. Amber has been at Goddard full-time since 2008. Prior to her current role, she held a NASA postdoctoral program fellowship. She has been involved in NASA programs since her undergrad years, beginning with flying an experiment on NASA's microgravity KC-135 plane, better known as the Vomit Comet, for those of you familiar with that, in 2001. During graduate school at Arizona State, Amber received the NASA Space Grant Fellowship for Summer Studies, and in 2005 was awarded the 3-year NASA Harriet Jenkins Predoctoral Fellowship. Amber's research focuses on interacting and star-forming galaxies in the context of galaxy assembly, where she uses imaging and infrared spectroscopic data mostly from the Hubble Space Telescope. Her broad research interests include galaxy formation and evolution, galaxy mergers and interactions, physical processes induced by galaxy interactions, including star formation and black hole growth and emission line galaxies. If you're like me and you have no idea what any of that means, you're in the right place because Amber's probably going to tell us all about it. In addition to research, Amber's role with the James Webb Space Telescope Project Science Team involves working with communications and outreach activities. She participates in various public outreach efforts and has spoken at numerous schools, astronomy clubs, museums, like this one, and research societies in the DC area and nationwide. Amber also interacts frequently with the media, having done numerous live television interviews, media features for NASA, and has appeared on the History Channel, Spike TV, and the Late Night with Jimmy Fallon show during the Hubble Got You segment. She very much enjoys interacting with the public. Amber lives now in Glendale, Maryland, with her husband, Matt, and her 2 Great Danes and 1 cat, who I'm sure loves living with those Great Danes, right? Her love for all things air and space prompted her to become a pilot. She earned her private pilot's license in early 2013, and she's been an active yoga practitioner for years and teaches a volunteer yoga class weekly. And she is very involved in community and volunteer work and loves to cook. And somehow through all that, she finds time to visit Seattle for conferences and come talk to us. So since you're not here to hear me talk tonight, I'm going to turn it over to Amber. Thank you again for coming, everybody. Thank you, Amber, for coming.
Great, thank you. Thanks for that great introduction. It's so great to be here in Seattle. I really love this city, so it's a lot of fun to be here, and especially to be here in this fantastic museum. This is such a great place. I'm an airplane nut and a space nut, obviously, so it's just really great. I'm honored to be here speaking in this really great venue. So yeah, my 2 big loves in my life, besides, of course, my family and my friends and my dogs, really are space and flying. And I got my start, as you heard, in the small rural town of Bee Branch, Arkansas. It was a really small town, middle of nowhere. I had 28 kids in my graduating class. So it was a tiny little town, and I might have been bored had it not been for the spectacular sky. And that's really how I got my start in astronomy. I constantly had my gaze turned upward, and those stars called my name from a very young age. And I remember asking my parents, my mom and dad, you know, what are those stars? What's up there? Is there anything beyond what we can see? And I remember at some point, my mom looked at me and said, I don't know the answers to those questions, and you're just going to have to find them out for yourself. So that's how I got my start in astronomy very early on. So the reason I'm here at this museum, of course, my second big love, close second to astronomy, is flight. And I also credit my love for flight to growing up in Arkansas. I grew up very close to an Air Force base and a C-130 training area. And so there were these huge military aircraft constantly flying over at very low altitudes. And I would run outside as a kid and wave up to the pilots. And I'm pretty sure none of them ever saw me, but I like to think that they did. And so I kind of got that love for flight early on in my life as well. And so it's only been recently, though, that I have pursued that love of flight. I did my first solo flight in a Cessna 152 on November 12th, 2012, on a tiny little airfield in Maryland, and it was glorious. And then a few months later, I got my private pilot's license, and so that's a very happy me once I had my license. And there's no doubt that flying really gives you a different perspective on the world, especially flying at low altitudes. And in addition to that, flying just gives you this undeniable sense of freedom of taking to the air. And I really love that. So flying is definitely a passion of mine. And my husband trained at about the same time I did. We both got our pilot's license at about the same time. And our first flight together was to First Flight Airport in Kitty Hawk. So it was a pilgrimage of sorts for us. And this was our approach into the runway there at Kitty Hawk. A lot of fun. We bought a Cessna 182. So we own our Cessna, and we are having a whole lot of fun flying it around the country. So back to astronomy. You've heard how I got my start in astronomy. So now, today at Goddard, I study, as you heard, distant galaxies using mostly the Hubble Space Telescope. And so, Hubble, wow. So this year, 2015, we celebrate the 25th anniversary of Hubble. Can you believe it's been that long? And Hubble has, in so many ways, completely revolutionized our understanding of the universe. It's changed the way that we as astronomers understand space. But even more than that, I think on a more profound level, it's changed the way that humanity thinks about space. Before Hubble, people thought of space as dark and void. And after Hubble, people think of space as colorful and beautiful. And I think that very subtle shift in how people generally think about space is really profound, and it speaks to the significance that Hubble has had on our culture. And so one of the reasons that Hubble has had such a profound impact on science and on culture is because these missions like Hubble really get to the heart of our big questions. Not just our big questions as scientists, but our big questions as humans. The questions like, where do we come from, and how do we get here? And then, of course, the big one, are we alone? And so through the years, Hubble has observed every phase of our universe, from our sort of cosmic nearby backyard of the solar system, all the way out to further reaches of our galaxy, to star-forming regions within our own Milky Way. And then the iconic pillars of creation. These are pillars where stars are being born inside these dust clouds. And you may have seen, in connection to this conference that I'm here for this week, just this week, Hubble released a new image of the pillars of creation. How many of you saw that this week? Okay, good. Some of you did. Well, I'm going to show it again because it's stunning. So this image was taken in 1995. So this is 20 years later, after this initial beautiful image was taken. And Hubble sees this. And then in the infrared, Hubble sees this. And then this is a movie that shows, sort of starting with here with 1995, and how those images all sort of collect together. So this is visible light here. This is UV invisible light. And then it will fade again into the infrared. And so by looking at different parts of the electromagnetic spectrum, of course we get these different beautiful views, but we also learn a lot about the universe from looking at the universe in different wavelengths. And so after stars are born in these huge pillars, of course they live out their lives and they die. And this is an example of a stellar death and explosion. And stellar deaths are often quite beautiful. And then thinking about going outside of our own Milky Way towards other galaxies, looking at other galaxies, we now know, thanks to Hubble, that there are something like 100 billion other galaxies in the universe. And so this is a nearby one, a very famous spiral galaxy. that might look like the Milky Way if you could get outside the Milky Way and look back on it. We know our Milky Way has large spiral arms and a huge black hole lurking at the center. So galaxies sometimes get close enough together that they interact. So this is an example of a colliding galaxy. This is the antenna galaxy. And lots of really fun stuff happens when galaxies interact. So new stars are born. We think black holes might grow when galaxies merge together like this. And when galaxies come together in these cosmic dances, we are able to learn about how galaxies form and evolve over time. So in addition to standing alone, galaxies group together in groups and clusters. This is an example of a galaxy cluster. There's a lot of really fun things going on. So every point of light you see here is a galaxy. And if you look here, what you see here is sort of a stretched out galaxy. And if you look closely, you can see other little blue arcs all around this image here. And so what's going on here is that all of these galaxies are grouped relatively close together. And you have this massive amount of dark matter surrounding this cluster that you can't see, but we know it's there. And all this combined mass serves to create a huge cosmic lens. And so galaxies in the background behind the cluster are shining through, and their light gets bent and stretched and magnified as it passes by this massive galaxy cluster. So this is a really cool trick of physics that we can use to study distant galaxies in much greater detail. And then if I had to choose my favorite image of all of Hubble's images, and they're all beautiful and wonderful, but if I had to pick a favorite, this would be it. So this is the Hubble Ultra Deep Field. This actually came out when I was in grad school, so it was very good timing for me. I got to do my dissertation research on this image. So in this particular version of this image, Hubble stared at one teeny tiny piece of sky for about 11 days. Okay, that's like looking at the universe through a straw. Okay, it's a tiny piece of sky. If you hold out your thumb, you could cover up that piece of sky. Okay, and every point of light you see here almost is a galaxy. So imagine multiplying that, right? And so it starts to give you a sense of how huge the universe is, of these hundreds of billions of other galaxies out there. And in addition to this image being just remarkably beautiful, what we can do is we can learn things from the light that we see, and we can assign distances to the galaxies based on their spectra. And so this movie illustrates real physical distances of the galaxies. And so once we're able to do that, you can start to view it in more of a 3D sort of way. And so here we see the galaxies that are flying by, and nearby, what you see, of course, are galaxies that you expect, spiral galaxies, galaxies with a lot of very organized structure, and maybe the big elliptical galaxies, the huge spheres of galaxies. But once you get further out, deeper into the universe, further into the past, what we see is a completely different universe of galaxies. You see, and you notice here, you don't see any more spirals, right? They're all gone. What you see are smaller, clumpy things, things that don't have a lot of organized structure. And this question of how we go from the small, clumpy things to the big, organized things is still an open question in astronomy. There's a lot about that process that we really just don't know about. So that's one of the things that I'm really interested in my research and that I work on. So that's just a very short review of all the awesome things that Hubble has done in its past 25 years. And this meeting here in Seattle, it's the American Astronomical Society meeting, is sort of the kickoff for this year of celebration that we have for the Hubble Space Telescope. And so I want to show you a video that NASA's put together to sort of as a teaser video to highlight some of the things that we have coming up. And I'm going to play that now. excited to celebrate this awesome milestone of this amazing machine this year. So if you're on social media, follow us with that hashtag on the bottom, Hubble25. And we have a new website that's just come up that's dedicated to sort of collecting all the events and the things that we have going on. So keep an eye on that. It's Hubble25th, Hubble25th.org. So keep an eye out for that, and there will be undoubtedly things going on here in Seattle in the month of April, which is the launch anniversary. So just be on the lookout for that. We have lots of fun stuff planned. So that's Hubble. Hubble's amazing. We're focusing on celebrating the amazing history that we've had with Hubble, but we're also talking about its future. So Hubble's in really good shape. The last servicing mission to Hubble was in 2009, and it got new instruments. It was basically completely refurbished. And so we expect Hubble to keep working out until 2020 or maybe longer. So we're excited not only about the past of Hubble, but about the future of Hubble. And one of the things that I think is so great about Hubble is its images obviously capture people's imagination and capture the public's attention, but also the fact that astronauts have been there to service it 5 times. These are heroes, right, that have been up to fix the telescope and make sure that it's been able to work for the last 25 years. So we're excited to celebrate Hubble, and I always like to point out that this is your telescope. If you're a taxpayer in the US, in a very real sense, it's your telescope. All the images that I've shown you tonight, all the videos, all the data that Hubble has ever taken is freely available online. A lot of people don't realize, but anyone in the world can go and write a proposal to use Hubble. So in that sense, it's very much an open source observatory. And everything that Hubble has done is available. So we love Hubble. I love Hubble. But we do have to start thinking about what's next. And of course, that's what I'm really here to talk to you about tonight. So this next video will preview.
Under construction is the premier telescope of the next decade. A next-generation space telescope designed to cause yet another giant leap forward in our understanding of the cosmos. It will carry some of the most advanced technologies ever placed on an orbiting observatory.
18 articulated mirror segments, 2.75 times the diameter of Hubble's primary mirror. Microshutters, wavefront sensing and control subsystem, 12 by 18 meter, 5-layer captain-based sunshield.
The Webb Telescope, a revolutionary tool able to study every phase in the history of our universe.
The Webb Telescope.
So that's it. That's what's next. So I always like to highlight, we say that JWST, the Webb Telescope, is the successor of Hubble, and it definitely is. So I like to highlight differences between Hubble and Webb to help you sort of understand what this telescope is going to be like. So the first big difference is the size. So Webb is big. It is by far the largest observatory that we've ever put into space. This is a full-scale model of the telescope, so just steel and plastic, not the real thing, obviously. This is set up at NASA Goddard, where I work. I am not in this picture, unfortunately. This was taken before I got there. But you can see that the telescope itself is huge. These are sunshields, which I'll describe a little bit more in detail later. But those are about the size of a tennis court, and the whole observatory is about 4 stories tall. So it is amazingly huge. Of course, one of the most important things about a telescope is the size of its mirror. Hubble's mirror is 2.4 meters in diameter. Hubble itself is about the size of a school bus. And then Webb's mirror is about 6.5 meters in diameter. And the reason the size of the mirror of a telescope is so important is for two primary reasons. First of all, is just the bigger the area of the mirror, the more light you can collect. You can think of it as a light bucket. And then second, the larger the mirror, the more fine detail you can see, the sharper the images will be. And so this big mirror is going to allow us to tackle some of the biggest questions in astronomy today. The second big difference between Hubble and Webb is the type of light that Webb will see. So Hubble is primarily an optical telescope. It sees the universe in visible light that your eyes see. Hubble does have a little bit of near-infrared capability, which you saw in that new image of the Pillars of Creation. Webb is going to be primarily an infrared telescope. So it will observe the universe in infrared light. And the reason for that is completely driven by the science questions. So all of the big astronomy questions that we want to answer today really demand an infrared telescope in space. And I'll talk more about why that's the case in a minute. So the third big difference between Hubble and Webb is where Webb is located in space. So Hubble orbits the Earth about 350 miles up. Webb is going to be located 1 million miles from Earth out at a point called L2, the second Lagrange point, which is a gravitationally stable point in the Earth-Sun gravity system. So that's a place where it's just good to put spacecraft. And NASA and ESA have put spacecraft out in that part of space before. So Webb will be 1 million miles away. And then we will, since Webb is so big, we can't put it into a rocket fully deployed. So we have to fold it up so that it goes into the rocket, fold it up, and then it will deploy once it's in space. So that, as you can, actually I've got a better video. I'm going to click past that one. As you can imagine, this is a very complicated matter. There is some really incredible engineering that's gone on behind this telescope. And I'm a scientist, so I'm excited to get the data back from this telescope. But the engineering behind this is remarkable. Northrop Grumman, as you saw, is our prime contractor. So this shows the deployment sequence after launch. So we start the deployments about a half an hour after we launch, so fairly soon. The first things to come out are the communications antenna and the solar arrays so we can get power. And then down on the bottom here you can see the sort of the distance from the Earth, and then there's the moon, and you'll see as it takes its trip out to L2. So a lot of complicated deployments. Along the way, we have to start, or we have thrusters where we can sort of do course corrections along the way. So I'll just let you kind of watch this as it happens. This is a really great animation that, that Northrop Grumman did for the project. So there's our antenna deployment. And then the second mid-course correction. So these mid-course corrections are planned, and of course we have a very precise orbital procedure that we go through on launch. We're launching from French Guiana, from close to the equator. This project is a partnership between NASA, the European Space Agency, and the Canadian Space Agency. The European Space Agency is providing our launch vehicle, an Ariane 5. And so their launch port is in French Guiana, so that's why we're launching from there. And the Ariane 5 is a very, very reliable heavy lifter. So we're confident about that rocket and very excited for launch in 2018. So what you see coming down now are the pallets that hold the sun shields that I had mentioned before. And then on top, of course, is the mirror, which you can see is all folded up. And then behind, so you see the three mirrors here. Behind the mirror is where the science instruments will sit. And then here starts the deployment of the sun shield. So the sun shield has these membranes that cover it up to protect it from things that go on during launch. And then the sun shield itself, you'll see in a second, will separate, and it's 5 layers. The sun shield's made out of kapton, which is a very thin plastic material. The whole story of the sun shield is incredible. So this material, this kapton material, obviously is not made in tennis court-sized sheets. And so there's miles and miles and miles of seams, of stitching in these sun shields. So just the manufacture of the sun shields is an incredible thing. And so you see how the sun shields have rolled out on each side, and then they're tensioned, and then they're separated. So here shows the 5 layers being separated. And the reason for the 5 layers is for heat dissipation. So the sun will always be down on this side of the telescope. The mirror will always be pointed away from the sun. And you get heat dissipation between each of those layers there. And so the top is very cold. The reason we're putting JWST into deep space is because it's an infrared telescope. Infrared light is basically heat radiation. You can think of it that way. And so we want to detect faint infrared signals from the distant universe. And so we don't want the telescope itself to be warm, or it would just see itself. It would see its own glow. So that's the reason we're putting it out into deep space. So the telescope itself can get very, very cold. Of course, we get constant radiation from the sun. That's why we have the sun shield. So the sun's always down on the bottom, and the sun shields protect the mirrors and the instruments from the radiation from the sun. And then the last big deployment that comes out are the wings, the mirrors, the 2 side wings of the mirrors. And all those deployments happen over, about 20 days. At about a month, the observatory gets out to that region of L2, and then it will actually orbit around the L2 point. And once we get out there, we'll have a few more months of commissioning, of checkout of the observatory before we're ready for science. So we'll be ready for science observations about 6 months after launch. So that's our deployment sequence. You can find this online on our website. Again, really complicated, but really wonderful stuff. So again, I'm a scientist. I want to tell you about some of the science goals that we have for Webb. So the first big science goal is to see the very first light in the universe. So this again is the Hubble Ultra Deep Field. And if you look really closely, in these images, we've been able to see some of the most distant things in the universe. And it's hard to see, even on this big screen, but there are these teeny tiny little red dots. And the most distant galaxies that we can observe with Hubble are these tiny little red dots. And what that tells you is that if you want to see, and so the reason they're red is because the light has been redshifted. And so the universe is expanding, and so the light waves stretch out, so longer light waves are redder, so the galaxies are more red. So with Hubble, we've sort of come up to a limit. We can only see so far back in the universe with Hubble, and those are these tiny little red dots. So if we want to see things that are more distant, we have to look at light that is more red, and that's what infrared light is. So that's one of the main reasons we're building this observatory to be an infrared observatory, is to see the first galaxies that were born after the Big Bang. So obviously, we've never seen them before. This is a completely unexplored territory. But theorists, theoretical astronomers, use physics and math and computers to build simulations to tell us what we think happened in those very early epochs of the universe. And so this is a computer simulation that shows how we think those first luminous sources formed after the Big Bang. Again, we haven't seen this part of the universe yet, and so there's a lot about this that we just don't know. And so a lot of what Webb will see will be, I think, surprises. But we do expect us to be able to kind of see past that veil that we're currently not able to see. And this infrared capability of this telescope will allow us to see very much further back into the universe to see some of the most distant galaxies that there are. So the second big science theme, the second thing we want to do is to watch galaxies assemble over time. So you remember I mentioned before that the distant galaxies look different than local galaxies. And that question of how that happens is still an open question. So this is, again, a computer simulation showing 2 galaxies colliding. And there's a lot about this process that we don't know. Studying this process of galaxy evolution broadly in infrared light, again, is going to help us to learn a lot more about how this whole process of galaxy evolution happened. We also think this process of galaxy merging is important for black holes growing. We know that all massive galaxies have a black hole at their center, And galaxies undoubtedly in the early universe were undergoing lots of merger activity. So this is probably a really important part of how black holes grow over time. And then the third big science goal is we want to see stars being born. And again, back to this iconic image of the pillars of creation, we know stars are born inside these huge dust clouds. And this is a visible light image. It's going to fade to infrared. And here, what do you see? You see the stars inside become visible in infrared light. And so infrared light has a unique capability to peer through dust and to see inside these pillars so that we can actually see the star formation going on. And then the fourth big science goal is, I've mentioned I study galaxies, so this is sort of far from my area of research, but I think this is one of the most exciting things that Webb is going to do. It's going to study other worlds. And so another big thing that was just announced this week at the astronomy conference was the detection of several hundred new exoplanet candidates, so planets orbiting other stars that are probably in their habitable zone. So small rocky planets in their habitable zone. So NASA's Kepler telescope is the telescope that's making all these amazing discoveries. And this is the very basic way in which Kepler detects exoplanets. So it stares at stars and it watches for the light to dim. And if the light dims on a periodic timetable, that means a star is passing by, right? It's orbiting. So that's how Kepler detects planets. And from these very basic observations, we can determine things about the planet, like how far it is, how big it is. But there's a lot about the planets that we can't determine. And that's why we need Webb. So what we really want to do is study the atmospheres of these exoplanets and find out if there's oxygen there, if there's water there, if there's methane and carbon and all the other elements that are needed to produce life, right? Because ultimately, that's what we're looking for as astronomers, is we're looking for planets that could be habitable and perhaps in the future planets that are inhabited. And so this is really hard. Studying the atmospheres of planets is really hard because stars are bright and that planets are tiny and their atmospheres are tiny. So this is an image from a few years ago of Venus passing in front of the sun. It's a real image from one of NASA's solar observatories. And obviously, Venus is not a habitable planet. It's very close. It's close to its star, to the sun. And if you squint really hard, what you can see is a teeny tiny atmosphere here on Venus. And so you see the challenge, right? To see that what's going on in the atmosphere and the glare of the sun. So doing this is really, really hard. But with Webb, we're going to have the very first chance to start to do this in detail. So really, really exciting science prospects for JWST to study exoplanet atmospheres. So the good news is that we're building it. And so now I want to show you hardware. So you saw all the images, all the videos of the telescope. And so the mirrors are one of the most iconic parts of the telescope. These are just testing images, or images of some of the tests that we've done with the telescope. This is at the Marshall Space Flight Center. This was a big cryovac test that we had on the mirrors. So the mirrors are shipped to NASA Goddard out in Maryland in these very space-age-looking pods. As of last year, we've gotten all of our flight mirrors into Goddard, so they're all there, they're all ready, they're finished. The mirrors were one of the hardest things to do for this telescope. The telescope is so big and the mirrors have to be perfect, and materials change shape in cold, right? And so the mirrors themselves are made out of beryllium. And so making and polishing mirrors on Earth in our temperature to be perfect in a cold temperature is a really hard thing to do. But we've done the testing and all the mirrors are ready to go. And they all meet their specs and they've all been delivered to Goddard. This is a test article of the backplane structure, so you can see where all the mirrors here will fit on this huge structure. People here for scale, again, just to sort of get a sense of how big this thing is. A lot of the hardware has been developed now, has been manufactured, and so the next few years are going to be testing and retesting. So this is a practice mirror, a practice backplane, just a little section of it, and a robotic arm that was built specifically to assemble the mirrors onto the backplane. And all these tests were done at NASA Goddard. And this is a flight version of the sun shield. And then this is a movie showing, and these are test membranes of the sun shield. This is out at Northrop Grumman in California. And obviously a time-lapse video, right? They don't move quite that fast. But again, what you can see here, you can start to get a better sense of the scale of the size of this enormous telescope. And so this was the first test that we had done of all 5 layers, the deployment testing. And so you can see some of the details of that going on here. So very exciting times. This was done just a few months ago, very recently. Oops, I skipped one. So behind the mirrors, I mentioned, is where the science instruments go. So this is the huge structure that houses the science instruments. And so every piece of this observatory, as we build it, all the individual pieces have to be manufactured and tested, and then they're integrated more. So pieces of the puzzle are put together and they're tested again. So this is the structure that holds the science instruments that goes behind the mirror. As of this last year, we've accepted all 4 of our science instruments. So these are pictures of our 4 science instruments at Goddard. This is an installation of one of the science instruments, again, on that black cage structure that I showed before. And here's another orientation of the instruments mounted onto that structure. And so those are then placed inside a huge cryovac chamber that we have at Goddard. So we put the instruments in there, we suck out all the air, and test the instruments in the cryo conditions of space. So down around 10 Kelvin. 10 degrees above absolute zero. So this is in the Goddard clean room right now. So this is called the Pathfinder. So this is all test material. This isn't real flight material yet. And so this has all happened just within the last few months. And so what you can see here is the middle section of that back plane. So the 2 wings are missing. And then the secondary mirror is all the way up here. And then these 2 mirrors were placed with that robotic arm. So these tests have all happened within the last several months, so very significant milestones for the telescope. So that chamber that I showed you before is not big enough to test the whole observatory, and so what we're going to do is take the mirrors and the instruments down to Johnson Space Center in Houston and test them in the huge Chamber A. So that's the chamber that was used to test the Apollo-era spacecraft. So that chamber has been completely refurbished and updated to accommodate JWST. And this is showing just some work and some test stands going on in this chamber very recently. These images just came out a few weeks ago. And so again, here, this is the door for the chamber, right? The whole chamber goes up. It's huge. It's enormous. And so you can, again, see the scale. This is the door, and here are the people. Massive telescope, massive test chamber, lots of big stuff. It's a really fun engineering project to be a part of. And just one more image of the mirrors here. So that's it. We're building the telescope. We are on track, on schedule for a 2018 launch, October of 2018. This is such an amazing project to be a part of, and I just feel so privileged as an astronomer to be on the team that is working on this amazing piece of machinery. And I want to invite you all to follow us, to follow along on the journey. That's our website, and if you go there, you can find all of the ways to connect on social media. All of the images I've shown you tonight are on our Flickr page, so there's a link for that there. All the videos are on YouTube. I don't know if you can see it in the back here, but on the front page of our website, we have a webcam where you can actually watch the work going on at Goddard live all the time. Well, maybe not right now. There's not people working there right now on the East Coast. But you can watch work going on there. And lots of other great information. So please follow along with us online as we complete this incredible journey up to launch in 2018. Thanks very much.
So if anybody has any questions for Amber, go ahead and raise your hand. We're going to carry these microphones around to you when we bring you the mic. You can ask your question, and we'll go from there. We'll go ahead and start on JD's side of the room over there.
One question per person, please. Here we go. thank you for taking the time to come and give this presentation to us. You have a very unique Twitter address I saw. Very
Yes.
good. My question has to do with the primary mirror. What is it made out of, and how can it be damaged and repaired? I guess it's just those two parts.
Okay, so the mirror segments, so the hexagonal segments, there are 18 of them in the primary mirror. Those mirror segments are made out of beryllium. So beryllium is a very lightweight metal that holds its shape very, very well in cold temperatures. So that's why we picked that metal to make the mirrors. And then the beryllium blanks are coated in gold. So the reason it looks gold is because it is. And the reason it's coated in gold is because gold is a good reflector of infrared light. So that whole mirror, the whole 6.5 primary mirror, is coated in about a golf ball's worth of gold. It's a microscopic coating, very, very thin coat of gold. So that's what the mirrors are made of. The mirrors, all of them have on the backs of them, which you couldn't see, but they have hexapod actuators. So they have these machines on the back that allow them to move in like 7 different degrees of freedom. So once we're on orbit, we'll take some sample images and get a crazy image back where you see all the funny kind of artifacts of having 18 different mirrors. And then we'll move the motors to make the mirror perfect. Okay? So we don't have to worry about a Hubble-like flaw. And then the answer to your second question, or the related point, is that we can't service it. At 1 million miles away, that's much too far for humans to go, for sure. The observatory was not designed to be robotically serviced. So one of the reasons we have such a huge timeline for test is for that very reason, is that we can't go and we can't go repair it. So we tested it every single phase to make sure it works like it's supposed to once it gets into orbit. And you know, when people think of Hubble, of course, they think of the astronauts up on Hubble fixing it, which is great. I mean, that's part of one of the endearing things about Hubble. But Hubble is really an exception to the rule in that sense, right? All of our other satellites that we depend on for our daily lives, for our DirecTV and our cell phones and everything, you know, those are built to work like they're supposed to once they're in space. And so that's the sort of method that we're using with this telescope. So no servicing, we're building it to work like it's supposed to once it gets into space.
Great. Another question right over here.
Along those lines, what is the risk for kind of micrometeorite damage at that point? And what are some of the repercussions there? I mean, you touched on the repair issues, but I guess another question, as I was thinking about, I'm no more than an amateur astronomer, but you talk about kind of being able to see back to the very earliest stars and galaxies. Without having the knowledge of astronomy and physics, could you see, you could never see the Big Bang itself. You can't go that far back. I mean, or is it Moore's Law? You just keep going further and further back as time goes on. So two questions.
Okay. First question, micrometeorites. So as I mentioned, so there are micrometeorites out in space. As I mentioned, there are several other NASA and ESA missions, satellites that are out in that part of space. And so we use those to help us learn about what the micrometeorite environment is out there. And so we have models, you know, we have models of the solar system that help us learn about that. And so we have a good idea of what the micrometeorite situation is in L2. And it's okay, it's fine. You know, the mirror and even the sun shield can take little pocks from micrometeorites, no big deal. Now, if something this big comes along and smacks us, we're going to be in really big trouble, right? That's a bad day. But the likelihood of that happening is really small. So we're not too worried about micrometeorites. Your second question about seeing back in the universe. So I mentioned in the beginning there are lots of different ways to observe the universe in different wavelengths, right? So the reason when I say that we're able to look back in time, essentially, is because of the fact that light has a finite travel speed, right? Okay, and so it's actually, it kind of blows your mind to think about that we are able to see into the past, but it's really simple and it's really fundamental about physics, is that light has a finite travel speed. You know, the light in the back of the room takes a teeny tiny fraction of a second to get to my eye, right? The light from the sun takes about 8 minutes to get to Earth. So we're essentially seeing the sun as it was 8 minutes ago, right? So you extend that back to objects further out in the solar system and further out in the universe, and light's taken more time to travel to hit our telescopes. And so in that sense, we're seeing objects in the distant universe as they were longer and longer ago. So because of the galaxy's redshift, which I described a little bit, we've hit a wall with Hubble. We can't see any further. And so with Webb, we're going to be able to see that first epoch of galaxy formation, or the epoch of formation that we can't see right now. Now, as far as seeing back to the Big Bang, so that's difficult for a lot of complicated reasons, but we can see back further in the universe. So NASA's COBE and Planck satellites have seen the remnants of the cosmic microwave background radiation. So that's a different part of the universe. At that time, there was no galaxies, there were no structures, but that's sort of the imprint of the early universe. So in looking at different wavelengths, we can see different things. But with Webb, what we really want to see is the first galaxies. And we know that happened at I'm going to go into astronomer speak here, at a redshift of, somewhere like, above redshift 10, which is where we can see now, okay? So it's further than that. But we're building Webb to see those galaxies that are just beyond the veil of what we can see with Hubble. That was sort of a long-winded answer. I hope it helped.
So I know I saw some hands on this side of the room. Is there anybody over here who had a question?
So you talked about and you showed images in different parts of the electromagnetic spectrum. I wondered if there was an agreed upon convention for how you color the images to bring it into the visible spectrum to make it consistent across images?
Yeah, so maybe possibly a related question is, will Webb's images be beautiful like Hubble? So the answer is yes. There's a little bit of art that goes into making Hubble images anyway, right? So the way it works with astronomical images is we take, so the reason there are colors is because we observe in different discrete bands, right? Different wavelengths. And then here on Earth, with our computers, we assign red to this wavelength and green to this one and blue to this one. And when we combine them, then you get those beautiful colored images. And so we can certainly do the same sort of thing with Webb's images and with really across the whole realm of the electromagnetic spectrum. So if you look at, if you go online and look up NASA images of X-ray images, right? X-rays, you can't see X-rays with your eyes, but you can assign colors to X-rays and learn about what X-rays are telling us about the universe. Same thing with gamma rays and infrared light and radio waves. And so yeah, there are definite ways that we can visualize all of this data, and we do that. And on the question of will Webb's images be beautiful, my simple answer is yes, absolutely. They'll be stunning. They'll be better than Hubble. And a sort of precursor to that is Spitzer, right? NASA has the Spitzer Space Telescope, which is sort of like this big. It's a less than a meter size infrared telescope, and its images are beautiful or stunning. So, and Webb's images will be something. Webb will be something like 100 times more powerful than Hubble, kind of generally. And it'll be like 1,000 times more powerful than Spitzer. So it will be remarkable. The images will be beautiful, and the science that we learn from this will be stunning.
Okay, another one back here.
Thanks. Can you describe the 4 instruments on Webb, and will Webb be equipped with a coronagraph to do the exoplanet observations you described earlier?
Yeah, so just very quickly, the 4 instruments, they span a wavelength range of 0.6 to 28.5 microns, so from sort of the visible red out to the mid-infrared. So we have NIRCam, near-infrared camera, which is the primary imager, NIRSpec, which is our near-infrared spectrograph, and this one, yeah, I could spend an hour just talking about it because it's remarkable. It has this amazing system of microshutters to allow us to do spectroscopy. And so, okay, so I have to talk about spectroscopy for just a minute. So, because this in astronomy, these images are gorgeous, but where the real good science is in spectra. And so I've been to ground-based telescopes where you go and we get spectra, and what we do is we literally take a metal plate and cut slits in the metal plate where the galaxies will be on the field. And so then the slits disperse the light into a spectrum, okay? Obviously, when you're in space, you can't, send up metal plates with slits cut in them. And so we have a microshutter array, which is this array of teeny tiny magnetically operated doors that can open and close on orbit. And so you can set up your slits in that sense. So that was probably way too technical, but just go and read about the microshutter array. So that's near spec. Our third instrument is the mid-infrared instrument, and that one, obviously, the imager, spectrograph, and IFU, that is geared towards the mid-infrared part of the spectrum. And then we have an instrument called NIRIS, which is a near-infrared imaging and slitless spectrograph, which is a mouthful, but it's another imager and a spectrograph all built into one. Yes. I saw one way in the back.
Their next question is going to be in the back here.
How long do you think Webb is going to be in space?
That's a great question. So we are building Webb to last, in NASA speak, an absolute minimum of 5 years. And we expect it to last 10 years, 11, maybe even longer. So what limits the lifetime of the telescope is the fuel. Okay, and so once we get the telescope on the rocket, we have a certain mass limit. We can't get any heavier than a certain point. But once it's on the rocket, we'll fill up the rocket with as much fuel as we can. And then if we get a really super efficient launch and we have extra fuel left over, we can keep using that fuel later on. And that fuel is used, if you remember the video, once we get out to that part of L2, it kind of makes this big orbit around L2. And so we use the fuel to sort of keep it in that orbit. And so once we run out of fuel, we won't be able to keep it in its stable orbit and deploy it anymore. So we're hopeful for 10, 11 years, maybe longer.
Another one right here.
All right.
Hi, I was just wondering why you named it the James Webb Space Telescope.
Where are you? Wave at me. Oh, there you are. Okay. Yeah, okay. I wanted to be able to see you. Yeah, good question. So James Webb was the second administrator of NASA. He was the leader of NASA during the development of the Apollo program. So he was responsible for getting men on the moon. So that's a little weird, right? Because this is an astronomy telescope. So the other crucial thing that James Webb did was that, a lot of people at that time thought that getting to the moon, it was a political thing, right? It was the space race. And so NASA was building rockets to get men to the moon. And so James Webb said that in addition to building rockets, that NASA needs to be about science. And so he really instilled that value of scientific research in NASA early on, in NASA's early days. And so he's a worthy namesake for this awesome telescope.
Okay, we have one right down in front here.
As the Earth turns beneath the moon, there's significant gravitational effects that we notice on Earth. Over a period of a month, the moon will circle the Earth so that it'll be, when it's towards the sun, it'll be about 500,000 miles further away from the James Webb Telescope. And then in half a month, it'll be 500,000 miles closer to the James Webb Telescope. So I wonder, will the moon have any noticeable effect, the gravitational pull of the moon have any noticeable effect on the James Webb Space Telescope?
No, it won't. So Webb is far enough away from the Earth and the moon that there won't be any significant effect. So the moon's about 240,000 miles away from the Earth, and so Webb is 1,000,000 miles. So that's about 4 times further away. And so yeah, we're not concerned about the gravitational effect of the moon on the observatory.
I'm in the same spot right here, right up front.
Hi, thank you. I was just curious, you said two of the main things that you're hoping to achieve with the telescope is to look at galaxies colliding and stars forming. I'm sure that's not something that happens over the course of a week. And so could you just give a 10,000-foot explanation, just a basic explanation of exactly how you study something like that?
Sure. So yeah, the movies I showed of the galaxies colliding and the process of star formation, you're right, those galaxy collisions take billions of years, right? So you're right. So the way that we as astronomers study these processes that take billions of years is by looking at galaxies, kind of snapshots of galaxies in the different phases, right? Okay, so we can look in the universe and actually see, there are two galaxies that are sitting here that are close together, and then we can look at another two galaxies that are close enough that they've started to sort of gravitationally interact, and you can see these wisps of stars and gas that that show us that they're interacting. And then you can see galaxies in a later phase of that interaction where they've actually smashed together, like the one I showed with the beautiful pink star formation going on. And so at the end of the day, it ends up being sort of a statistical game where we take samples of galaxies, in this case, in different sort of stages of their formation, and then we have to it's sort of a big puzzle, and we have to piece all that information together to figure out how that process happens over time. And yeah, we're talking billions of years, right? The universe is 13.8 billion years old. So it's a lot of work. That's a lot of fun, yeah.
And we have one right down in front here.
Hi, thank you for spending all our tax dollars so well, by the way. I was wondering if you could kind of separate yourself from the science and the responsibility and everything like that, and kind of get in touch with that childhood wonderment you had when you were looking up at the stars, and you think about this project. And if you can let yourself go, what kind of surprises, would be like incredible to dream of, and what do you think we might find?
Yeah, what a great question. So, just generally, for me, one of the coolest things about being a scientist and one of the coolest things about working on missions like this is that there's no doubt that every time NASA launches a big, bold mission like Hubble or like Webb, that we learn things about the universe that we never dreamed. It always happens, right? Hubble was a big part of learning that the universe is accelerating, right? That was a huge surprise. Nobody expected to find that. So absolutely, I'm certain that once we launch Webb, we'll find things that surprise us. We have all these very set, specific questions that we set out to answer, and that's great. That's how science proceeds. That's how we build telescopes. But I'm sure there'll be things out there that surprise us. And this Webb is definitely the next step on finding habitable planets. But we're not promising that we're going to find a habitable planet, right? It's not quite big enough to do that, okay? But it could. And if there is that Goldilocks planet that's close enough that we haven't seen yet, that would be it. That would be the blow your mind sort of discovery with Webb. Or again, who knows? And that's one of the most fun things about science is who knows what we'll find. There are surprises out there that we haven't even dreamed of yet.
And we have one more in the center of the room here down in front.
Hi, good evening. Hang on to that kid moment, because I've got two with me. I'm just the driver. If I understood your timeline correctly, the kids in junior high and high school today will be the ones in graduate school studying the first images from Webb.
That's absolutely right.
What advice would you give those kids to be ready?
That's a great question. I would say, first of all, just if you're excited about it, just keep up that excitement, right? Science is all about discovery. It's about keeping an open mind and staying inquisitive about the universe. So I would say do things you love. Astronomy is my thing. I love astronomy. But if your thing is building things, then pursue engineering. Or if you like, studying animals, be a marine biologist. Just do what you love. That's the biggest piece of advice that I can give. But then specifically, if you do like science and want to become a scientist, there's the standard you should take all the math classes you can. take all the science classes you can. And then beyond that, one of the biggest things for me, kind of early on in high school and then afterwards, was being able to find mentors, find cheerleaders, find people that support you and can help you and are as enthusiastic about your goals and your dreams as you are. So that's been really important to me along the way. So just keep up your enthusiasm and excitement, and you can do anything you want to do.
One more over on this side here.
Thanks for your presentation. I hope I'm allowed 2 questions. The first is, you say this device will be orbiting a spot in space. I gather it will not be orbiting any body out there. What's the purpose of the orbit? And my second question is there any element of this research that might lead to discoveries about dark matter?
Okay, good. 2 good questions. So the first one, it will not be orbiting any body. So L2 is sort of an imaginary mathematical point in space. So Lagrange was the mathematician that figured out that there were all these different stable and semi-stable points in the overall gravity system of the Earth and the Sun. Okay, so L2 is the one that's way out on the other side of the Sun. L1 is between the Sun and the Earth. And then there are other ones along the Earth's orbit. Okay, so this is just a mathematical, physical thing that happens. It's these gravitationally stable points, physics and math. So L2, there's nothing there. In a mathematical sense, it's a saddle point, so it's an unstable point. So that's why we need fuel to keep it in the orbit. So yeah, it's just going to be orbiting this imaginary kind of gravitational point. But at the same time, it orbits the Sun along with the Earth, right? So it's always, so you can sort of think of it as it will always be straight up in the midnight sky. Okay? And then your second question, dark matter. Yes, we'll learn things about dark matter from this telescope as well. And dark matter was another one of those sort of weird surprise discoveries. You know, we looked at galaxies, at the way galaxies were rotating, and figured out they don't rotate like they should based on what we see, so there must be more stuff there. And dark matter is this huge mystery. You know, we don't know what it is. Same thing as dark energy. You know, astronomers have this really great habit of, if they don't know what something is, they call it dark, right? Dark matter, dark energy. But we definitely expect to learn more about these, about dark matter and dark energy with Webb. And that's another thing that sort of ties back into the, you know, the surprises question is, you know, everything I've shown you tonight, all the galaxies, all the stars, all the hardware, all the people, all the planets, make up something like 5% of the energy matter content of the universe. So the rest of that, the other 95%, is dark matter and dark energy. We don't know what it is. So everything that we see, everything that we know is a teeny tiny fraction of what exists in the universe. And that alone is just astounding, I think. So.
And it looks like we got one more in the middle there. That's going to about do us on time for tonight. This will be our last question.
Is there any plans to do any study on the black hole in the center of our own galaxy to get a better understanding of it?
So my short answer to that is I'm actually not sure. So I study distant galaxies, so I don't know, but I would imagine so. So I definitely know that there are plans to study, you know, star formation within our own galaxy. So I'm sure that the Milky Way's supermassive black hole must be a target for study. A lot of black hole study is done generally throughout the universe is done with X-rays, but we can definitely learn things from infrared light as well. So I would imagine that is in the plans, but I don't know the details.
Okay, and I'm going to just sneak one in real quick that I've been curious about, Amber.
Sure.
Hijacking my own Q&A here. How confident is Northrop Grumman that all those steps of deployment are going to go off without a hitch? And what kind of contingency plan is there if, say, you know, the wing mirrors don't come out or something along those lines?
Okay, so again, I've already mentioned that we can't service it. The reason NASA picked Northrop Grumman to build this is that Northrop Grumman is the world's leader in deployable optics. They tell me they've done things that are harder, but they can't tell me what they are. So really we do have the world's best engineers working on this. And a lot of the different sort of individual deployments that you see have backup systems, right? So if one motor doesn't go off, there's a backup motor that we can operate. And we do all those deployments, you know, from Earth, right? Yeah, we're sending commands to the telescope to tell it to do the deployments. So we really we're trusting the engineers that are the best engineers in the world that are working on this project. So we're confident that the deployments will happen like they're supposed to. So 2018 is going to be an amazing year. And you know, when the Mars rover landed on Mars a couple years ago, which was awesome, right? Curiosity is amazing. Did any of you see that 7 Minutes of Terror video? Right? That was a really good video. So we joke that we're going to have, like, you know, 7 weeks of terror why these deployments are happening. But no, really, we have the best engineers in the world working on it, and all the testing is going great. So things are on track and on schedule for 2018 launch. So we're excited.
Excellent. We're all hoping for the best for you. Thank you, Amber, so much for coming down to the museum tonight.